All right, I want to talk about Pascal's triangle. This is a neat little tool that's going to make it a lot easier for us to verify that the power function rule works. But it's just neat on its own too. So let's just revel in it. Let's look at Pascal's triangle and see how this works. So we're going to start with what I'm calling row 0, which is just a 1. And I want you to think in the background that it's really 0, 1, 0. Row 1, we've got two ones, and we'll see how we can attach this to some polynomials in a second. And this will really, at least for me, really comes alive. So we've also got these zeros on the outside here. So we're building a triangle, and there's going to be a triangle of zeros, and there's going to be a triangle of ones. Normally people don't draw the zeros, but for me, I like to think of them as really being there because fundamentally what we're doing at each step is we're taking two numbers and we're adding them up. And 0 plus 1 is 1. That is a legitimate answer. So as we build out Pascal's triangle, we're going to have these ones going off on the diagonals. But I really think we've got these zeros, this vast expanse of zeros, and we're building up from nothingness into somethingness. So we add these up. Now, when we go to here and we add them up, we're going to get something different enough that I'm going to use a different color. 1 plus 1 is 2. 0 plus 1 is still 1. 1 plus 1 is 2. So now we've expanded from one term to two terms, plus those imaginary zeros there. One term to two terms to three terms. And we're going to go to four terms, right? And we're going to keep adding terms here. So we could really call this row 1, but I'm going to call it row 0 for good reason. So let's keep going. 1 plus 2 gives us 3. 2 plus 1 gives us 3. 1 plus 3 gives us 4. So now we got another pattern. We got these zeros and the ones that are just constants down either side of the triangle. And now we're going to have 1, 2, 3, 4, 5, and so on. Right? 1 plus 4 is 5. We're going to have a 1 plus 5 is going to give us 6. 3 plus 3, we've got 6 and a 4. 10, 10, 5. We got those ones on the outside. 1, 15, 20, 15 again, 6 and 1. And now we are at what? This is row 1, row 2. So we're going to row 7. And row 7 is a really 7-y row. 6 plus 15 gives us 21. That's 7 times 3. 15 plus 20 gives us 35, which is 7 times 5. 35, 21, 7, and 1. So what do we got? We got 7 times 1, 7 times 3, 7 times 5. We don't have that here. We don't have 6 times 2. We go from 6 to 15. That's why row 7 is just extra 70. That's a nice little thing to experience there. That it's purely aesthetic. It's nothing at all to do with the math that we're going to be doing. So row 0, row 1, and so on. Now, how do we use these in binomial theorem? Well, there's the binomial theorem itself, but really what I'm concerned with is expanding terms that look like x plus y to the power of n. So x could be anything, right? It could be some messy thing. This could be, 37 xy plus 2x squared minus y square root, right? It could be any number of weird things going on in there. But if we can find a way to split it apart into x plus y to the power of n, right? We got this to the power of n. If we can find the way to structure this right, we can use Pascal's triangle to figure out what the terms are going to be. Now, this is a mess, so it would be much easier to say something like, we're going to call this x, call it x hat, and this will be y hat, and we'll figure out for x hat plus y hat to the power of n. We're not going to worry about that. We're just thinking really in these simple terms, x plus y to the power of n. So let's say we've got x plus y to the power of 1. Well, if we look in row 1, we could see 1 and 1, and we could just say 1 times x plus 1 times y. Well, hey, that's the expansion. We got it out of the parentheses. If we go to row 0, this is why I like these terms, this row numbering, instead of calling it this number as actually I am calling it this number as the row, but instead of saying this is row 1 and 2, which has 2 terms, and then row 3 is the one with 3 terms, instead saying we're going to start from row 0, well, if we look at x plus y to the power of 0, what does that equal? Well, that equals just 1, right? That is our default 1, right? It's nothing at all except 1 more than that. All right, so now as we go down, we've got x plus y to the power of 1, x plus y squared. Okay, well, this is something that I can do pretty easily. Right? We're just doing FOIL, first, outer, inner, last. And I could do that even if I had cubed terms, right? It would just take a little bit more time. But what I'm going to get here is x squared plus xy plus xy plus y squared. Right? X squared, there's the y squared, there's the xy, and there's the other xy. This is x squared plus 2xy plus y squared. Or really, 1y squared, 1x squared, and 2xy. And that's what we get in row 2. 1x, 2xy, 1y. Now there's another pattern we're going to layer in here to make this really nicely encapsulate all these possible expansions on these terms. So let's say, well, let's take a look at row 3. So x plus y to the 3. X plus y, this is the last one I'm going to do manually. So we're going to have x times x times x gives us an x cubed. We're going to have a y times y gives us a y cubed, which I'm going to put over here. We're going to have an x times a y. We've already said x times x times x, so we got xy. We're going to have an x times a y times an x, and we're going to have a y times an x times an x. Right? We can kind of see how the possibilities, the set of possible combinations that we can multiply through, first, outer, inner, last, captures everything, right? But here, what are we going to have? We're going to have a bunch. And I don't want to try and figure out exactly how many. I'm just going to split it up like this. So 2 x's and a y, well, then there's also going to be 2 y's and an x, plus yxy, plus xyy. Right? So we're going to have 3 in each of them, so we can have 3 x's, but there's only one way to get 3 x's. We could have 2 x's and 1 y, and there are 3 ways to get that. And hey, check this out, 1, 3, 3, 1. So this is the same as 1 times x cubed plus 3x squared y, right? 3 versions where we have 2 x's and a y, plus 3 versions where we have 1 x and 2 y's, plus 1 version where we have 3 y's. Now here's that other pattern, right? We had x squared, xy, y squared. Now we've got x squared, x cubed, x squared, x to the 1, x to the 0. Y to the 0, y to the 1, y to the 2, y to the 3. So what we're going to end up having is 1 times x to the n plus some term times x to the n minus 1 times 1y plus some term times x to the n minus 2 times y squared, and so on all the way down till we've got 1 again of y to the power of n. So we're just counting the exponent up by 1 in one direction and down by 1 for the other term in the other direction. Now, it doesn't matter here if I'd called this y cubed plus 3xy squared plus 3x squared y plus x cubed. Again, the order doesn't matter, but having an order is going to be useful if we're thinking about terms down here. And so if we want to say, what do we get for x plus y to the power of 7, we're going to have an x squared plus 7. Sorry, not x squared. I don't know why I'm putting the squared out there all the time. X to the 7. We're going to have 1 times x to the 7 plus 7 times x to the 6 y to the 1 plus 21 times x to the 5 y to the 2. And we're going to get 21 over here too, except now it's going to be x to the 2 y to the 5. We're going to have 35 of x4, y3, x3, y4, x2, y5, x1, y6, x0, which is just 1, times y to the 7, right? X to the 0 equals 1 for any value of x, which is just a nice little extra element. When we bring in zeros, zeros are beautiful, and they're invisible, and they're not really doing anything. In this case, they're turning something into a 1, but they just make the pattern complete. It just kind of fits into place. So that's, again, we can throw in extra zeros. I like the extra zeros. Now, why do we care? Well, we're going to see this trick in a separate video, but what we can see here is, given something, right, we're going to be looking at something along the lines of x to the power of n. So we're going to be in the nth row somewhere, and we're going to end up with, well, we're going to want to look at, x plus h to the power of n when we're doing the derivative, right? So this is where we're actually going to be doing this binomial expansion. So by having this general pattern, we're going to be able to see something that is going to be true for any value of n, and it has to do with this pattern of how we always have 1 with x to the power, y to that power, or in our case, h to that power. And then we go down 1, and we have some number, but we have some number multiplied by 1h, right? Or h to the power of 1, h squared, and so on. So when we factor out the h's, which we'll see what that means in a second, that's going to allow us to say something about why the second term turns out to be important. Let's break here, and we'll come to that as a separate video.